Next, let's just try to picture the sign of a few definite integrals. So here's the setup. I want D, that's going to be the region in the xy plane, and that region is going to be given by the area inside the unit circle. So I've tried to draw this unit circle in blue in the xy plane. And in this first example, I want to integrate over that region, and I want to integrate under the surface given by z equals y squared. So z equals y squared is this parabolic cylinder that extends along the x-axis. And notice in particular what's important is that it's always positive. So it would be very messy, but I'll try to draw a couple rectangular bars. There are rectangular bars that live above that unit circle and go up to the surface. So imagine the whole unit circle being filled with these rectangular bars whose heights are given by the surface z equals y squared. In particular, notice that they're all positive. Since they're all positive, the volumes of each of those bars is positive, and so the sign of this definite integral is positive. Okay, this next example is a little bit different. So the region over which I'm going to integrate, the unit circle in the xy plane, is the same, but this time I'm going to integrate the surface given by z equals y cubed plus y to the fifth. So notice that y cubed plus y to the fifth is not always positive as it was in the first example. And in particular, if y is positive, so in the upper part of this circle, well, if I take positive numbers and I plug them in, I'll get a positive output. So I get a quote-unquote positive height for each of the rectangular bars that live in that region. On the other hand, in the lower part of the circle, down here, if I plug in a negative y value, these terms will both be negative, and so the heights of each of the rectangular bars will have a negative value, okay, but they'll cancel each other out. I'll get the same positive contribution from the positive y part of the plane equal to in magnitude the negative contribution from below the x-axis. So those will simply cancel each other out, and this definite integral has a value of 0. So continuing with that previous example, if we just change the region over which we integrate a little bit, instead of taking the whole unit circle this time, let's let B be the bottom half of this unit circle. So that's this unit circle. And just as we discussed before, the values of y cubed plus y to the fifth, these are all negative inside B, inside the region B in the xy plane. And so when I add up again, these are not really heights, but the quote-unquote heights are all negative. Okay, so when I add up all those values, this time the value of the definite integral over the region B is negative. This final example looks a little funny because there's no function, or at least there appears to be no function, but it turns out to be a pretty important example. So this is the integral over the same region B, which is the half circle below the x-axis on the negative y-axis, and the integrand is just dA. So what's really happening is that the function is 1. So every rectangular bar that I draw above the region in the xy plane will have a height of exactly 1 everywhere. So every single rectangular bar will have exactly the same height. So you can imagine that what I'll get is a surface that looks exactly like the image that's in the xy plane, and so and since the height is exactly 1, I think you can convince yourself that what this is going to be exactly equal to the area of B, only because I've put in the integrand a 1. Okay, so the volume is the area of the base times 1. So multiplying by 1 only changes the units, but if I ignore the units, this definite integral gives the area of B. Okay, so I can actually answer this question exactly. this area is just half the area of a circle, and since the radius of this circle is 1, this definite integral is equal to 1/2 pi, and clearly that's positive. This final example is much like the first example that we had, only there's a contour diagram instead of a table of values. But the question is to find an estimate for the definite integral over the region R of f of x. And let's think about the region and read it carefully. So it says the region is the rectangle that goes from x equals 0 to x equals 30, and then goes from y equals 0 to y equals 15. So it only wants me to use part of this picture. So I want to find the volume. I said area again. I want to find volume of the surface that's above this rectangular region in the xy plane. And further, this example says take an underestimate. So it gives me more instruction than the first example did. So here's what I'm going to do. And further it says use delta x equals 10 and delta y equals 5. So what it's telling me to do is to use subregions in the xy plane that have an x width of 10 and a y height of 5. So I'm going to use 9 rectangles in the xy plane, and over each of those I'm going to determine the height of the rectangular bar that goes up to the surface of the function f of xy, but I'm going to be careful to take an underestimate. So on every bar I'm going to pick essentially the smallest z value that I see. Okay, so here we go. So I'm going to estimate the integral over r of this function dA, and let's start with this bottom left-hand corner. So it has a width of 10 and a height of 5, so the area of the base is 50. And for a height, I'm going to pick 2. Certainly there's a smaller value down here somewhere, it would appear, but I'm just going to go with 2 for simplicity. So I'm going to multiply by a height of 2. And then I'm just going to work my way through the other 8 rectangles. Each subregion in the xy plane will have an area of 5. The height in this second rectangle I'm going to take to be 4. So I'll multiply by 4, plus 50 base area for the third rectangle, times a height of, let's go with 6 right down there in the bottom left-hand corner. So times 6. Plus, then we'll move to the second row, 50 times in this rectangle. It looks like 4 maybe just barely touches it, so I'll multiply by 4, plus the middle rectangle. I'm going to go with a height of 6, plus the right rectangle in that row. I'm going to go with the height, I'm just going to go with 8. It looks like it goes lower, maybe even down to 7, but I'm just going to pick the lowest contour line that I see and multiply by 8. And then finally the top row, 50 times, I'm going to go with 8 again, very, very rough estimate. The middle rectangle, 50 times 8 again. And finally in the upper rectangle, I see 8 just through that corner, so I'm going to call it 8 again. And that's my estimate. So again, as with the first example, you can simplify life a little bit by factoring out the 50 and then adding up what's left, or distributing it out. So we get 2 plus 4 plus 6 plus 4 plus 6 plus 8 in the middle row plus 3/8 in the bottom row. Okay, and then if you work all that out, you get an estimate for the volume of the volume of the solid that's under the surface given by this function and above this region in the xy plane.